Hello everybody, my name is Tsering. I come all the way from Minnesota and I go to the College of St. Benedict and St. John's University. This is my REU at UTD under the guidance of Professor Eric Wong. The topic I chose is called Metamorphic Testing of MNE-Python software, created by Mutation testing. So without further ado, let's dive right in. So, in the beginning, starting with MNE-Python, it is the field standard open source toolkit that scientists use to clean and analyze electroencephalogram or EEG and MEG or magnetoencephalography brain recordings. Generally put, scientific software is often written by domain scientists rather than pure software engineers. So software may not be fully tested in the most practical way. I want to explore and seek software like this, which is why I landed on MNE-Python and hopes to find issues or bugs in an impactful package. Along with that, I learned about an issue with software testing, about the test oracle problem, where sometimes when testing, the user may not know what the correct answer is to test for. So the plan was to utilize metamorphic testing to help spot and improve on current testing suites provided. And also, on the left, if you see down, you can see how it's like a basic example of a MEG/EEG recording, where it's kind of the data is stored as frequencies. Before going more in depth to help give the viewers more context, I want to give an overview of what this presentation entails. Firstly, I'll be answering what is metamorphic testing, then what is mutation testing, along with that, how MNE-Python data is stored. And then after that, I'll be going more in depth with the actual experiment with research question and objectives, related works, methodology, the setup, results and discussion, and lastly, the conclusion and future work. So, first of all, metamorphic testing is a property-based software testing technique which can help against the test oracle problem. This involves running multiple executions of the software. Now, the most straightforward example is considering sine of pi minus x being equal to sine of x. Now, imagine you're creating a program and you're trying to implement sine of x to the nearest 100 significant figures. You may not know what exactly it is for whatever value you may put in. However, this relation that we know is true can help us solve this. Like for example, if we let x equal 1.23, you can simply plug it in for x on both sides, and you may not know what the correct answer may be. Because you have this relation, as long as both of them end up being equal, which is a true relation, you know that the program would work. Looking at a more practical example, however, a brain recording is really just a grid of numbers, one row per electrode, and one column represents a moment in time. So average re-referencing works by subtracting at each moment in time the average across all the electrodes. The main idea is that we don't need to know the correct answer, so to say, just that both answers are the same or consistent, and that's really what metamorphic relations are and what we'll be utilizing. So then we talk about mutation testing. It is a fault-based software testing technique that measures the effectiveness of the test suite by injecting intentional bugs or mutations into the source code. When testing code, if it passes, it could mean the code is correct, or the test is too weak to notice anything wrong. If the existing tests fail when the bug is brought in, the mutation is killed, proving the test works. If they still pass, the mutation is considered to have survived, showing off a gap in the test coverage. Now, it answers the question whether those tests are any good, and I'll be planting thousands of small bugs in MNE and then running my relations against each one and seeing how many of those they actually catch, which helps to measure how good my tests are at catching bugs. However, it doesn't prove the code is bug-free, as we will get to later. So, how the data itself in MNE-Python is stored. Now, like I mentioned earlier, it is really just a brain recording, or not just a brain recording, it's really just a grid of numbers where every row represents an electrode or sensor. As you can see in the top right, there's like about around 100 or so of these sensors or electrodes, and every column would represent like a moment in time for the frequency. So MNE normally carries out, or has like 3 ways to store this data, whether it be raw, which is just the full unfiltered continuous recording, nothing changed, an epoch, where it's just a short snippet cut around each stimulus, or evoked, where it's a lot of the snippets are just averaged into a singular clearing response. And just for the audience to know, we will just be looking at EEG and MEG, as MNE-Python has a lot of other different ways, different methods of recording brain recordings, or just looking at brain recordings, and EEG is recorded in voltage, and MEGs are recorded in Teslas. So let's talk about the research questions and objectives. For our objectives, I spent some time looking at the core operations in MNE-Python. There are a lot of different operations, and I will tell you later on what 4 main ones that I looked at. And using these metamorphic relations, I will see whether or not it works on unchanged code, and then use the mutant testing to then inject small faults into the MNE's source code, and then measure how many of each of the relation catches, and then compare it to how many of the MNE's own test suite does compared to that. And so for our research questions, I'll be answering RQ1, do the relations hold for correct MNE? RQ2, what fault detection rate does each achieve? And then RQ3, do they catch faults MNE's tests miss themselves? Now, before the results, a quick word on where this all fits and why it's worth doing. None of the things that I'm doing individually are necessarily new on their own. Like the test oracle problem is, not knowing the right answer to test against. It's already well documented. And metamorphic testing dates to the late 90s, and its mutation testing is really, it's also not that new. And there's even a paper that combines them exactly as kind of like how I do, where relations are graded by mutation testing, but it's for image processing and not brain data. So people have tested scientific software as well, and the closest work was ran by mutation testing on a library built on top of MNE, but it was with generic automatic bugs only, and never had relations written for MNE itself. So that's the thing. I'll be combining multiple things and then just essentially applying it to a domain that hasn't, or a niche that hasn't been really utilized, because there isn't really any for metamorphic testing done on MNE-Python. So let's talk about the methodology, right? Now MNE does a lot, so I scoped this to 4 operations that almost every study runs. First of all, there was bandpass filtering, where you're just throwing away frequencies you don't want, like electrical hums from the building or slow drifts from the electrodes. And as you can see, there's like 4 different metamorphic relations that are like tied to it, which I will list later. I'll list them off later. Then there's resampling, where you just change how many measurements per second you really keep, whether you go from 600 like snapshots down to like 300, right? Just ways of like storing data or saving data. Then there's average re-referencing, where it's specific to EEGs, where it only measures the differences in voltage. So every number is relative to some reference point. Re-referencing, it re-compares each electrode against the average of all of them. And then there's the baseline correction, where you subtract off what the signal was doing before the stimulus, or when the main activity was going on in the brain. So what's really left is the actual response, and so we're just really kind of paying attention to that. And of course, on the right side, I'll just list them off. For the metamorphic relations, there's scaling, linearity, DC invariance, time shift equivalence, channel permutation, average reference, common signal cancellation, resampling, and baseline window. These are all just like the relations that are connected to each of the four main operations. But then, in addition to that, I later added on two synthetic ground truth checks to kind of like, in a way, what was it? It helped feed the filter in for two tones, one that should pass and one that should be blocked, and it checked the right one would survive. The other one would send a tone in with a known size, and it checks it. It comes out the same size. So it was kind of like a way to catch certain things that I thought would have otherwise not. Of course, so here's how the experiment was set up. It was tested with MNE-Python 1.12.1 with the four core operations, looking at filter, resample, rereference, and baseline. There were the 8 metamorphic relations with our synthetic ground truth checks. The input had a seeded synthetic array, so there wasn't any like real data set used, and I could have utilized it. But that's for later on, future work. And then there was an injection layer with the fault injection or the mutation testing had 2 layers. One was the generic, you're changing small things in the code. This was done with Cosmic Ray and target specific source files. And then I had my 6 operators that I made, that was made more so intentionally to mimic what is likely to happen when a programmer makes a mistake in the code, right? Where it's like you could have a sign be flipped the wrong way, have the wrong units, stuff like that. Anyways, so for our first question, do the relations hold on correct or unmutated or unchanged MNE code? Unsurprisingly, it's very straightforward. They all worked, right? I mean, as you can see in the image, like every single test sort of worked on the baseline or the control group, which was sort of expected. So now for the second question, the fault detection rate. With Cosmic Ray and everything like that, they implanted like 2,256 generic mutants, and within that, we had about 34% for baseline, 44% for filter, 42% for resample, 44% for re-reference, and so it was about like 43% on average. So it's nothing like, it was nothing that impressive. But the more interesting thing isn't really the number. It was that the rules turned out to be overlapping heavily, right? I expected 8 of the 8 rules to kind of have their pulling their own weight, but really, for most of the operations, it was like one really strong rule that was doing most of the work, while the others were really catching the same bug over and over again. So a lot of the times the rules do really well on the actual maths, and it did really poor on the code that checked whether the inputs were valid. That's where most of the survivors hid, and it was like it was a gap in what I tested, not really a flaw in the idea. So, like I said earlier, part of the experiment was that I was to test these domains, the 6 domain or more of the man-made faults, right? And then see whether or not these relations can sort of like catch them. And of course, they were all caught, right? But there were some issues with like the unit scale and the wrong cutoff, where all 4 of the relative relations associated with them sort of missed them. But I guess as a result, the structure preserving faults are usually like a blind spot for this sort of issue. That's what I found. So for our third question, whether or not the faults that our relations catch that MNE's own test suite can sort of miss. If you look in the chart, you can see that usually the red would have indicated like the original testing that I did, right? And it seemed really good at first, where it looked like, oh, 5 bugs that my own relations caught, where the other test suite kind of sort of missed, which I thought was a good thing. However, there's an issue for the testing of how it was done, because MNE's numeric reference tests were gated on its optional. It needed that sort of like testing data set, because like I said earlier, I used like a synthetic data set, and I didn't really use anything at all for that. So because of that, it skipped the 5 generic mutants, which sounded good. I mean, it did not. It was not. It was just a mishap on my part. And so after retesting by adding in the extra optional data set where I brought it back in, it also went back to a 0 out of 75, so it wasn't really that good. But if you look at baseline, it says 6 out of 56 for both of them, which you may think that's good. It's really not, because that means both. It was just a testing mistake that both of them sort of missed. So looking back and for the discussion of why MNE's own tests kind of sort of beat, or it was our own relations weren't better. It was more so the fact that I was looking at the wrong direction. It was a flaw in looking at the core operations that I chosen, because it turned out that like there really was an exact answer for it. So when the true answer does exist for something, any sort of metamorphic relation you can come up with, it's a subset of the actual true answer, right? So whatever I could have done for my relation, if there's an actual true answer to compare it to, it would have gone for that. And usually it'll be listed on the slides as I've shown, as you'll see, but they all follow like the same pattern of like the 4 correlations were not like they didn't have like a weak oracle, so to say. So as it's shown here for like 0 to 150 for our filter, it's listed there. I won't really read it out. Same thing for our the 0 out of 163. Same thing for our 0 out of 75. So the 6 bugs or issues are listed right here on this slide, and it kind of entails what was changed and what exactly that 6 were missed, the bugs that kind of survived. And usually these are the types of bugs that are like that really, it changes the code to where it's changed, but it doesn't really affect the overall like code. It doesn't really affect the code, so to say. It can still operate, right? So looking at the exact 6 bugs that both sort of missed, right? Initially, the first 50 that were caught, it was used by a 4-sample 1D array. However, the other bugs, for some reason, they ended up counting it as a 2D array, and so it kind of just sort of ignored those bugs entirely, right? Which was a flaw in itself. And along with that, it's believed that 4 of 5 are caught by MNE's other more broader baseline testing cases anyways. So that's sort of like an issue with the metamorphic relation. It's not something to be done by itself. It's great for to be used in addition to other testing methods, right? Which is what MNE-Python already has. So as you can see on the right, it's kind of just mentioned what really happened there. So along with that, the relations that were formed, they end up being sort of redundant, right? For our filter and within filter, with our scaling channel permutation relations, they have like the identical kill sets, about the same amounts. So they both sort of contributed to not any unique any kills, right, for the bugs. So dropping both leads to like nothing being changed, right? And so for resample combined, it led to like 163. So what really mattered was that there wasn't it only helped a lot when there was this absolute check, right? And so relative relations are largely redundant with, they can be redundant with one another. So it helped having that exact answer to check too. So lastly, this is the most important slide with the conclusion. So what was really delivered was a reusable metamorphic relation library and a first mutation testing and measurement for the MNE's operations. A measured boundary where metamorphic testing helped and where it got dominated or not really used as well. And for limitations, it really helps for metamorphic relations if you sort of understand the software itself from in and out and kind of know where the oracle problem kind of shows up, right? For me, for myself, I really wanted to learn the software. It was from the get-go, which was, I'd say in hindsight, not the best idea if you're trying to pair it with metamorphic testing. So that was a big hindrance for my results and effectiveness. And of course, it doesn't really work effectively if there's an exact answer to actually compare it to, right? Which is where I'm going back to the results of 0 out of 150, 0 out of 165, 3, and 0 out of 75, right? So, but for the next steps, I mean, if I really wanted to, I could look at the more core operations where metamorphic relations are required, because there are, I'm sure. It's just I had to spend more time looking for that, or I should have spent more time looking at that. And then, yeah. And lastly, I just want to show references here, and thank you. That's all I have to say.